Hello everyone, and welcome to Euclid Book 1, Proposition 6. So this is sort of the flip side of Proposition 5. So in Proposition 5, we started with an isosceles triangle in the sense that we knew the two sides were the same length, and then we derived proofs about the angles. Here in Proposition 6, we start with information about the angles, namely that the two base angles are the same, and then we derive the fact that if that is true, the triangle is isosceles. In other words, that this side must be equal to this side. So it's sort of Proposition 5 run in reverse. Again, it's an argument proposition, so the picture doesn't matter as much. It's a logical argument sort of a thing, but a good picture can help you. So here I have drawn a triangle, and I've gone ahead and labeled the angles. For me, it's 68 degrees on both sides. Yours doesn't need to be 68, of course, but just to show you that in this triangle, indeed, these two angles are equal. Okay, now I can go ahead and delete that. And then let's run the proof. So Euclid says, Proposition 6, if in a triangle, two angles be equal to one another, the sides which subtend the equal angles will also be equal to one another. So in other words, if these two angles are the same, then the sides subtending those angles, which would be this one and this one, are also the same. So let ABC be a triangle having the angle ABC equal to the angle ACB. I have that already. I say that the side AB is also equal to the side AC. In other words, Euclid's going to claim that, hey, that means this length is also equal to this length, which of course is correct. But now he's going to run a sort of reductio ad absurdum proof where he assumes that's not true and derives a contradiction, thereby proving that in fact it is. So Euclid says, for if AB is unequal to AC, one of them is greater. That should make a whole lot of sense. If this line is not the same length as this line, then one of them is bigger than the other. Well, yeah, yes, of course it is. Okay. So then he says, let AB be greater. So let's just assume that AB is the bigger one. Okay, of course, it's not the case in this picture, but we're running that kind of contradiction proof here. So assume this is the bigger one, AB. And from AB, the greater, let DB be cut off equal to AC, the less. In other words, if indeed this line is bigger than this line, then we can cut it off somewhere. Let's say it's cut off right here, such that the distance from B to D will be equal to the distance from A to C. Should make a whole lot of sense. Okay? And then he says, and let DC be joined. So then he says, let DC be joined. Right there. Okay. And then he's essentially going to run now a sort of proposition 4 proof where he's going to consider two triangles. I'll read it for you, but let me go ahead and mark it just so you understand what's going on. He's going to argue that if indeed DB is equal to AC, then this little triangle here, right there, is actually equal to this bigger triangle right here, that they have the same area, in other words. But just from our picture here, it is obvious that they don't. The smaller cannot have an identical area to the bigger, and so that will be the contradiction we get. But he's going to argue that this smaller triangle is actually equal to the larger triangle if DB equals AC by using side angle side. So it's going to be basically side angle side on this guy, okay? And then remember, because we're assuming DB equals AC, it's also going to be on the other side here, side angle, same angle because the base angles are equal, side, of course this side is the same because they're both. And so that'll be a side angle side proof that the smaller triangle here has the same area as the bigger, but of course that's absurd because we can see just from this picture that in fact it has a smaller area, and so that's the contradiction that finishes the proof. But just to go ahead and read it, then since DB, right, is equal to AC, and BC is common, in other words, this lower line is in both the triangles I just mentioned, the two sides DB and BC are equal to the two sides AC and CB respectively. In other words, DB equals AC, which of course, so that's what we're kind of assuming in this contradiction proof that DB equals AC, and we're assuming that BC equals CB. Well, BC and CB are in fact the same line, so yes. And the angle DBC is equal to the angle ACB. So in other words, this angle, that was sort of the given of this whole argument. This angle right here is equal to this angle right here. Okay. Therefore, the base DC is equal to the base AB. In other words, therefore, this, which is the other side of the small triangle, is equal to this, the other side of the big triangle. Okay. The triangle DBC will be equal to the triangle ACB. In other words, the little triangle then has the same area as the big triangle. Okay. The less to the greater, which is absurd. And there we go. I mean, obviously, the smaller triangle here, which is just a piece, just part of the bigger triangle, cannot possibly have the same area as the bigger triangle. That makes no sense. Therefore, AB is not unequal to AC. Therefore, it is equal to it. So therefore, it cannot be the case that this line is not equal to this line. Therefore, it must be the case that they're equal, that in fact AB is equal to AC, and therefore if these base angles are the same, the triangle is in fact isosceles. And then Euclid says, therefore, etc., QED.